work titled Machine Learning Training on a Real Processing in Memory System. This is a work that we have developed in this Safari Research Group in collaboration with the ABMEM company. And let's start with an executive summary. Training machine learning algorithms is computationally expensive and frequently memory bound due to repeatedly accessing large training data sets. In that sense, we think that memory-centric computing systems, that are systems with processing in memory capabilities, can alleviate this data movement bottleneck. And as we are discussing today, there are real-world PIM systems that are becoming a reality, are starting to be manufactured and commercialized. And the first one of them was the ABMEM PIM architecture. Our goal in this work is to understand the potential of modern general-purpose PIM architectures to accelerate machine learning training. So, main contributions of our work are PIM implementation of several classic machine learning algorithms such as linear regression, logistic regression, decision tree, and k-means clustering, the workload characterization of these implementations in terms of accuracy, performance, and scaling, and the comparison to their counterparts implementations on CPU and GPU. We perform the experimental evaluation on a real-world system with more than 2,500 PIM cores and 158 gigabytes of PIM-enabled memory, of DRAM memory. Our work results in some new observations and insights. For example, ML training in PIM systems benefits from fixed point representations, quantization, and hybrid precision implementations. Complex activation functions, for example, sigmoid, can take advantage of lookup tables when these operations are not natively supported by the hardware. The data can be placed and laid out in the PIM core for the PIM cores to access the nearby memory banks in streaming, thus maximizing the PIM memory bandwidth. And ML training benefits from scaling the size of PIM-enabled memory with PIM cores. We are going to see all these different points. The outline, first of all, we are going to start briefly introducing the machine learning algorithms that we focus on. Then we will talk about processing in memory systems, these real-world processing in memory systems and common characteristics that they have. Next, I will discuss the PIM implementation of the ML workloads that we have targeted. Finally, we will evaluate them and provide some key observations and insights. So let's start with the machine learning workloads. So here, as you see, we have this kind of figure showing different machine learning algorithms, supervised learning, unsupervised learning, and reinforcement learning. We are focusing on regression, classification, and clustering, and in particular, linear regression, logistic regression, decision trees, and k-means. These algorithms require large amounts of data for training, and this is a computationally expensive process that requires many iterations. And in many cases, the frequent data movement so there is a frequent data movement between memory and the processing elements, and the amount of computation in the processing elements in the cores is not enough to amortize the cost of moving the training data to the processing elements. So this results in low arithmetic intensity, low temporal locality, and irregular memory accesses. And these characteristics can definitely benefit from processing in memory systems. For this reason, our goal in this work is to study and analyze how real-world processing in memory, general-purpose processing in memory systems can accelerate ML training. We focus, as I said, on 4 representative machine learning algorithms, and we characterize them for motivation as memory-bound workloads using the roofline model. As you can see, all these workloads fall in the memory-bound area of the roofline. So let's start talking about the processing in memory. You already know what's processing in memory. It's a paradigm that advocates for memory-centric computing systems, placing processing elements near or inside the memory arrays. And there are already some real-world processing in memory architectures from ABMEM, Samsung, SK Hynix, and Alibaba. And there are, among these 5 PIM systems, there are some common characteristics. The first one is that there is a host processor, either a CPU or a GPU, that can access standard main memory and PIM-enabled memory. PIM-enabled memory contains multiple processing elements with high bandwidth and low latency memory access. These processing elements typically run at a few hundred megahertz and have a small number of registers and a small or no cache or scratchpad memory. And these PEs also need to communicate via the host processor. This is how one of these state-of-the-art processing in memory systems looks. As you can see here, we have the host CPU with several cores and its deep cache hierarchy. This host CPU has access to a number of DIMMs of standard DRAM, of standard main memory, and also has access to the PIM-enabled memory. As you can see, these state-of-the-art PIM systems consist of memory arrays, and near the memory arrays, we have the PIM processing elements with their different components, such as instruction memory, scratchpad, or cache, and the ALUs or compute units themselves. In our work, we use the AppMem PIM architecture that consists of general purpose processing cores called DRAM processing units or DPUs. Each of them can run up to 24 PIM threads that are called tasklets, and they support 32-bit integer arithmetic, but they don't support multiplication or division. These operations are emulated, as well as floating point operations. Each DRAM processing unit, each DPU has access to its own DRAM bank called MRAM of size 64 megabytes, and also a small scratchpad called WRAM of size 64 kilobytes. So let's discuss the PIM implementation of the machine learning workloads that we are targeting. So as I said before, we focus on 4 widely used machine learning workloads: linear regression, logistic regression, decision tree, and k-mean clustering. And these workloads and their implementations on their PIM system are diverse in terms of memory access patterns, operations and data types, and communication and synchronization needs, as you see inside the PIM core, but also between PIM cores. For linear regression, a supervised algorithm, we use gradient descent as the optimization algorithm, and our PIM implementation divides the training dataset equally among the PIM cores. Inside each PIM core, we will have PIM threads computing dot products of row vectors and weights, and each dot product is compared to the observed value to compute a partial gradient value. These partial gradient values are reduced inside the DPU and then sent to the host. We proposed, or we implemented 4 different versions of linear regression. The first one is called LinFP32, handles training data sets of 32-bit real values, floating point. The second one uses fixed point representation. The third one uses hybrid precision. It starts computing 8 bits and then starts increasing the precision as it's needed. And finally, this LinGUI implementation uses custom multiplication. It's a custom multiplication that we design ourselves using built-in functions. Regarding logistic regression, a supervised learning algorithm used for classification, we use sigmoid as the activation function. Our PIM implementation follows a similar pattern, similar approach to the one that I have described for linear regression. And here we have 6 different versions of the logistic regression. The first one, LogFP32, it uses training data sets of 32-bit real values. And in this case, the sigmoid operation is approximated using Taylor series. The exponentiation is approximated using Taylor series. Then we have the login32, in this case, fixed point representation. We have another version, another fixed point version that replaces the computation of sigmoid. Instead of using Taylor series, uses lookup tables. And for this one, we actually have 2 different versions. The first one keeps the lookup tables in MRAM, in the large DRAM space of size 64 megabytes, and the second one places the lookup table in WRAM. Next, we have also a version with hybrid precision, similar to the one that we have in linear regression, and finally, the version that uses or custom multiplication. For decision tree, as you may know, decision trees are tree-based methods used for classification and regression, or PIM implementation partitions the training data set among PIM cores and computes partial Gini scores to evaluate the split decisions done by the host. This host sends commands to the PIM cores. There are 3 different commands that it can send. The first one is the split commit to split a tree leaf. Second one is a split evaluate to evaluate the split. And the third one is min-max to query the minimum and maximum values of a feature in the tree leaf. The different PIM threads inside a PIM core work on different batches of feature values and compare them to a threshold to update the partial Gini score. And in this particular workload, it's important to be very thoughtful about the memory layout, how we place the features in memory in order for the PIM threads to access the data in streaming, and this way maximizing the memory bandwidth. And the last implementation is k-means clustering, an iterative clustering method. In this case, what we do is, again, dividing the data set evenly over the PIM cores, and the PIM threads evaluate what's the centroid that is the closest one to each point in the training data set. After evaluating that, they update a counter and evaluate and update a counter and update accumulators per coordinate and per centroid, and then the host recalculates the centroids. Convergence happens when the updated centroids coordinates are within a threshold. So let's take a look at the evaluation of these workloads. Regarding our evaluation methodology, we use different data sets, synthetic and real data sets, and the systems we use for evaluation are the ABMEM PIM system with more than 2,500 PIM cores. We use an Intel Xeon Silver with 16 hardware threads and an NVIDIA A100 GPU. We evaluate quality metrics, performance of PIM kernels for a single DPU, a single PIM core, performance scaling across multiple PIM cores, and finally we compare to CPU and GPU. This is the PIM system that we have used in our evaluation. It's a system that can have up to 2,560 PIM cores or DPUs and up to 160 gigabytes of PIM-enabled memory. And this is how it looks here. You can identify the dual socket CPU, some DRAM DIMMs, and some PIM-enabled DIMMs. So regarding the quality metrics, the general observation is that our PIM implementations show very similar accuracy than the reference CPU implementations. Only the integer versions suffer a little bit, but still the accuracy is quite close to that of the floating point versions that's common in linear regression and logistic regression. It's interesting that in logistic regression, because in the loop-based versions don't use approximation but use exact values in the lookup tables, they obtain lower training error rates than the versions using approximations. And for decision tree and k-means, we essentially have the same quality results than the CPU versions. So regarding the analysis of PIM kernels here, what we evaluate is how the performance scales inside a single PIM core or DPU when we change the number of PIM threads from 1 to 24. That is the maximum number of PIM threads that can run on a PIM core. Several observations here. First one is that all of these versions saturate at 11 or more PIM threads. The reason is related to the characteristics of the pipeline of the DPUs or these PIM cores. That's something that we already observed in our previous work. The saturation point happens at 11 PIM threads or tasklets. Another interesting observation here is that the fixed point implementation accelerates the kernel by an order of magnitude, as you can see from this number here to this number here. The reason is that floating point operations are not natively supported, while integer operations are. multiplication and division are not, but this definitely alleviates the overhead a lot. But because multiplication is not natively supported in this hardware, we proposed as well or implemented as well a hybrid version that takes advantage of the faster multiplication that is natively supported. It's an 8-bit multiplication. And by using this hybrid version, we improve the performance by 41%. And the built-in, so the version with custom multiplication provides an additional 25% speed up. For logistic regression, we observe similar results. First, for the versions that use sigmoid approximation, we see that the execution time is extremely high, but that's because we are using Taylor series. When we move to the LUT-based versions, observe that the performance improved by 53 times from this log-in 32 version to the log-in 32 that uses lookup table in MRAM. The version with the hybrid implementation improves performance by an additional 28%, and the version with custom multiplication an additional 43% speed up. Regarding decision tree and k-means, first observation is again that the performance saturates at 11 or more tasklets or pin threads. And also something else is that for decision tree, the maximum number of pin threads that we can use in this case is 16. But because this, kernel, the decision tree, is quite intensive in the use of the WRAM or scratchpad, and because the scratchpad is quite small, the number of threads that you can run concurrently gets limited. But still, that's not a problem because even 16 or after 11 performance saturates. So no matter for performance, what's the number of tasklets or pin threads that we use between 11 and 16. Here in this slide, you can see some results for performance scaling. Particular, these plots are strong scaling from 256 pin cores to 2048 pin cores. One observation here is that the PIM kernel time scales linearly with the number of PIM cores. It's something that is good news. And also very good news is that there is very little overhead from inter-PIM core communication. Remember that this inter-PIM core communication needs to happen through the host CPU, and also very little overhead from the communication between the host, let's say initial communication between the host and the PIM cores, and final communication to transfer the results back from the PIM cores to the host. Regarding the comparison to CPU and GPU, the version, the implementations of linear regression and logistic regression, they use multiplication very intensively. So that's why they are not so good at this comparison, because these operations are not natively supported by the hardware, but still the different optimizations that we have applied have considerably closed the gap with GPU performance. And hopefully in future generations of this PIM architecture, we will see that this gap gets even closer. And for decision tree and k-means, it's quite good to observe that decision tree, for example, is 27 times faster than the CPU version and 34% faster than the GPU version, and k-means is 2.8 and 3.2 times faster than the CPU and the GPU respectively. So finally, key observations and insights. First of all, as you have seen, ML training workloads greatly benefit from fixed point data representation, quantization, and hybrid precision implementation. These ML training workloads that require complex activation functions such as sigmoid can take advantage of lookup tables in case that these activation functions are not natively supported. Data can be placed and laid out such that memory accesses of PIM cores are in streaming, and this way we maximize the memory bandwidth. And ML training workloads with large training data sets benefit from scaling the size of PIM-enabled memory with PIM cores attached to the memory arrays, as we have seen in our scaling results. To conclude the executive summary, machine learning or training of machine learning workloads is very computationally expensive. It's frequently memory bound, and that's the reason why PIM can help to alleviate this data movement bottleneck. Real world PIM systems are starting to be available, and that's why in our work we have focused on understanding the potential of modern general purpose PIM architectures to accelerate machine learning training. Our main contributions: the PIM implementation of 4 widely used machine learning algorithms, the workload characterization of these implementations, and the comparison to CPU and GPU. We perform the evaluation on a real PIM system with more than 2,500 PIM cores, and our study resulted in several interesting observations and insights that I just enumerated. If you want to read more or learn more, you can go to archive to the extended abstract that is already published there. And if you want to learn more about the ABMEM PIM architecture, you can go to this short paper that we published last year, or the longer version of it. Out of this paper, we generated a lot of micro benchmarks and benchmarks to characterize the architecture and study workload suitability of this ABMEM PIM architecture, and all of them are publicly available in our repository. And if you want to learn more about processing in memory, you can take a look, you can read this book chapter, A Modern Primer on Processing in Memory, or also watch the lectures of our PIM course that are available as well in YouTube. So that's all from my side. If you guys have any question, please let me know.
In one place, you talked about that the PIM system is not supporting that multiplication work. That in that place you proposed something. I missed that, but can you explain that one?
To alleviate the fact that there is no multiplication supported.
Yes, sir.
Okay, so yeah, well, I mean, I don't have many details here. The thing is that the current ABMEM hardware doesn't support 32-bit integer multiplication natively. They only support 8-bit multiplication. They have 8-bit multipliers. So the way that the 32-bit multiplication is currently implemented is by using the traditional shift and add algorithm that may take up to 32 cycles. So because the 8-bit multiplication is natively supported, it only takes 1 cycle, right? So what we did is creating a custom multiplication that uses this 8-bit multiplier, and in the end, the 32-bit multiplication results to be faster.
Okay.
Thank you for the question.
Hello, thank you for your presentation. My name is Fernando. My question is it's more like a concept question. The problem with machine learning training is that the algorithms are changing every day, basically. We have one day convolutional networks, the other day we have transformers. So how do you think that this impact the future generations of PIM? Because the good thing about GPUs is that you can just update a C++ code and then you have another function implemented that some mathematician described it. So how does you impact the future generation of the
Yeah, that's a very good question, a very good thought. I agree with you that machine learning algorithms are evolving very fast, especially deep neural networks. But there are 2 things to say here. First of all is that observe that we are not targeting deep neural networks in this work. And the reason is that GPUs have a prominent position in training of these kind of workloads. But still, I think that at least, for the precisions and data types that are being used these days in GPUs, this specific architecture, the current generation, is not the best one for the reason that we just discussed related to multiplication, but it could be better in the near future. What is clear is that this specific PIM architecture is not going to suffer from the possibility of getting updated because the models have changed. And the reason is that it's general purpose. You can program it. You can write whatever code you want, same as you can do on a GPU. But the problem that you pointed out, I believe that exists not only for processing in memory-based accelerators, but also other types of accelerators. If one architecture is very much specialized on a specific model or a specific network, it may turn out that in a few years is useless. That's why I think it's important and interesting to understand what's the potential of general purpose architectures. Thank you for the question. Okay, yeah. Oh, you also have a question, great.
Hi, my question is, you implemented 4 specific machine learning algorithms. Is there a reason to that? Why you chose them?
For this one?
Yes, why this?
I mean, the first reason is that they are widely used. The 4 of them, I believe, they're classic and widely used, are textbook algorithms. And the second reason is that we wanted to implement algorithms that we know in advance that can benefit from this architecture. That's same as I said before. That's why we are not targeting yet deep neural networks, for example.
Okay, thank you.
A really fast follow-up question to what Michalis asked. So I spotted that you didn't test it. For example, I'm not going to talk about random neural networks or something like that, about algorithms that are machine learning, like random forest, that include randomness. And the randomness in data-driven like algorithms like machine learning inherently has some the trade-off of performance and accuracy. Mm-hmm. So is this like, is the randomness, because we are talking about processing memory, like a nemesis of PIMs? Does is there like a trade-off between accuracy and performance? Because in the evaluation, I didn't see like any accuracy evaluations. And
there are indeed, and actually, I mean, you mentioned random forest that is is based on decision tree, right? And it's like
it's like a decision
tree, of multiple decision trees, and we evaluated in terms of accuracy, and that's what we observed, that the training accuracy is pretty similar. It's very close to the evaluated CPU version. So in principle, for this sort of algorithm, I don't see so much problem because we don't really need to reduce the precision. Decision tree is mostly comparisons, right? And even if you are comparing 2 floating point values, it's okay in this architecture because it's just comparison.
So yeah, I was mostly focused about the randomness that is inherent in random decisions, is like random forest or random neural networks, but your answer to that covered me. Mm-hmm. So yes, thank you.
Okay, thank you for the question. Okay, yeah, if there are no other questions, yeah, thank you very much for your attention, for staying.